Welcome to Astronomy, Chapter 12. This chapter is going to be called The Lives of Stars from Birth Through Middle Age. Now, before I get into this chapter, I want to say something about the title of this chapter. And that is, there is this analogy we're going to be using. And the analogy is something we call anthropomorphizing. We are taking stars in this chapter, and we'll again in the next chapter, and going to look at them as if they were a living thing. Now, stars are not alive. Stars are not a living, breathing organism of any type. They are not considered a biological entity. However, it is often useful for us to take this analogy and carry this a long way in describing the actions of how a star changes over time. It is very analogous to a living organism, especially a human, as we go from birth through a stable stage in the middle of our lives to the end of our lives when things are more tumultuous. But in this chapter, it starts off, we're simply going to be looking at the early stages and up through the stable part of the life, if you will, of a star. Now, I'm probably not going to say much of anything else about the idea of this life and death issue and the whole part of specifically stating that these things are not alive. But I will be using the description of life and death for a star, even with a bit of my own reservations, because I don't like saying something is alive if it's not alive. The star is not a living thing, but nonetheless, this is a very useful way to describe the change over time. So you will hear this throughout the next couple of chapters, this style, this method. So anyways, the lives of stars from birth through middle age. What we're going to be looking at, we're going to start off, of course, with, if we're talking about this process, if it's an evolutionary process from, birth to middle age, we should start with how do they form? Well, so if we're talking about about human beings, where do babies come from? Well, we need to understand what those are made out of. Well, stars are not made out of biological matter. In fact, they are made largely out of gas and dust, is how we're pretty confident these things start. The gas and dust exist between stars, and we see this all over the place. We have copious amounts of evidence. When we look at stars, we see these clouds around them. Lots and lots and lots of places. We see this sparse gas, and the term for this is a nebula. And the idea is that this is the matter that is going to or could become a star if the star were to be born. Now, the process of getting a star to be born generally is going to involve some sort of large, powerful act to kickstart this thing going. Now, remember, gravity is the major mechanism at play here. And gravity is an attractive force between anything with mass, and those little gas particles and those dust particles have mass. So they will draw in on each other, but something has to get it going. Right? Usually the usual idea for what we think starts most stars is supernovae, or some sort of collision or some sort of wave that pushes this material together. And once you get some of this material to move towards each other, gravity, the attractive force between those particles, is going to start pulling them together. And as they pull together, they're going to have more mass. And as they have more mass, they have more gravity. And you can see how this is going to sort of build on itself. And the idea is that these supernova remnants will continue to collect material in until it pulls together all of the stuff around it. And in doing so, at this process, this is what we call the protostar. Right? And a protostar, when it stops being able to suck in this stuff, when there's no more dust to pull in, or no more dust that it can pull in, it is what we call a pre-main sequence star. Right? And we learned about the main sequence back in last chapter, talking about the HR diagram. But the idea is there is a point where it can only pull in so much. Now, the next idea is a crucial one, because the idea of what happens to this star. Is it going to go off, and is it going to be a large, major, giant, like a bright, shining star in the sky? Is it going to be a small, easily missed dim star? Depends on its mass. It's mass that determines what is going to happen to the star. Now, the unit of mass we use here, we see a lot. We see this little M with a circle and a dot. The circle and dot means solar. So, okay, we're talking about here is, remember I said everything is related to solar masses. So we're talking about 5 solar masses or 1 solar mass. So when you're doing your reading through this, we're talking about how much mass does it have relative to the sun. So that is going to be the part that determines what's going to happen to it. Now, one of the things that we can do, a lot of times when we are trying to find age, we often rely on star clusters. Star clusters are important because they give us a big sample of a lot of stars that are at the same distance that are probably all formed together. So having a group of stars together in a star cluster ends up being very useful and allows us to figure out the approximate age of these things. Now, of course, when we're talking about stellar ages, we are talking about many times longer than a human life. You know, a human life is on the order of 100 years. You know, star lives may be on the order of billions of years. If they continue at a steady rate, you know, there are exceptions, but generally speaking, stars are going to be existing much longer than a human lifetime. So obviously, one person can't go out and observe a star form, grow to middle age, and die. It doesn't work that way. No human gets to do that. So what we do is we look for groups of stars, and we try to figure out how they go along together. Now, a great analogy for this that a professor told me once was, imagine this. You know, imagine you're at the Super Bowl, the biggest sporting event of the year, and you know someone was to take a snapshot of every person, every human being at that game. And if you were to look at all of those people, look at the entire population, you would be able to figure out which ones are roughly what age and roughly the lifespan of a human based off of looking at, you know, a sample of, you know, 70, 80,000 people. Same concept holds true with the stars. That's what we're trying to do. Take a snapshot of a big group and try to figure out what's going on amongst the whole group and to get general statements about what's going to happen to them. Now, I want to offer you a great diagram on page 391 that's really worth looking at. When they do these full-page diagrams, they're excellent. And this one is talking about how the star formation process goes. We have this dark, cold cloud. We have as it begins to condense and come together. It forms these protostars. The protostars are pulling in all of this material, and eventually they form. If they pull in enough material, they're going to compress and create enough heat to get the process of nuclear fusion going. Now, in doing so, there are going to be some stars that are going to be very large, and we'll talk about how those are going to end up at the end of the sequence, the end of the main sequence. They're very large. The other part that we're going to look at, though, is we can also look at what happens with small stars, where we're talking about 0.08 and to 0.4 solar magnitude of stars. What happens to them? Well, eventually, these are going to become a type of star we call a red dwarf. A red dwarf is giving you the two clues to what this thing is. Red, remember from the HR diagram, is cold. And cold, relatively speaking, as far as stars go. Dwarf means small. So we're talking about a small, cool star. And in doing so, these small, cool stars that do not have very much mass eventually convert all of their mass into helium, and that's about it. They have a very simple process. Red dwarfs are extremely predictable in that way. Now, when we look at stars that have more than 4/10 of a solar mass, they behave a little bit differently. And we see that there is the fusion slows down, and when they do so, there becomes a battle, so to speak. And what happens is, if there is not enough mass to continue fusing the helium, what happens is there will be a core of helium with no thermonuclear reactions. And what that means is, this is where this star is running out of gas. Effectively, that's what it means. It is running out of fuel. And in doing so, the center will cool off. And so what this does is, eventually, this star will become a red giant star after this fusion begins. And eventually, in the next chapter, we'll talk about what happens to this type of star. Something specific happens to this type of star after it turns into a red giant, based off of, again, all based off of mass. Okay, if we get much higher, we will get out of the main sequence, and we'll talk about what happens to those next time in the next chapter. But now, the last section in here gives you a little bit about variable stars. Variable stars are exactly what they sound like. If you were to imagine, a light switch, that has a dimmer on it, where you go up and down, up and down. It's exactly what a variable star is, where it has a change in its brightness, a significant change in its brightness. Now, for a long time, variable stars were not really noted. It was not necessarily very obvious that we could tell this variation. But it turns out, actually, the variable star ends up playing an essential role in our understanding of the universe as a whole, because it was a special type of variable star that was used by Edwin Hubble to be able to measure tremendous distances. Now, the variable star that was in question is called a Cepheid variable. And the idea is that these Cepheid variables pulsate and by expanding and contracting, expanding and contracting. And in doing so, that specific pulsing allows to measure, it turns into a new tape measure, if you will, to determine enormous distances. And so there's a relationship between how long it takes for it to glow and dim and glow and dim. And this that correlation is called the period luminosity relationship. And in looking at this, it allows us to figure out the distance to other galaxies. Ultimately, Cepheid variable stars were what were used to determine distances to other galaxies. All right? Now, that is about the end of what we're going to be looking at in this chapter. I'm going to kind of glance over the last couple sections after Cepheid variables. And that will get you ready for finishing up chapter 12. So make sure you do the reading through at least the first, looks like 13, 14 sections in this chapter. Make sure you're checking out the PowerPoint, keeping up with this class, and you should be ready to get going on that homework. Good luck.